Oh, it's more a timing.
The broadcast is now starting. All attendees are in listen-only mode.
Hello, and thank you for joining us today for the HDSA Lunch and Learn webinar series. This is Jane Krogan, HDSA's Education and Advocacy Manager. Today's webinar will focus on family planning and will be presented by Dr. Kim Martin. Before I invite Dr. Martin to begin, I'm going to go over how to ask a question as well as how to access HDSA webinars after broadcast. I'll also let you know about future webinar offerings. God, I'm so sorry. Please note that the information presenting is for informational purposes only. We will be answering questions after the presentation. However, you can send a question at any time. To send your questions, go to the right-hand panel that appears on your screen, type in your question, and hit send. HDSA webinars are all recorded and available after broadcast. You will be able to view this webinar in approximately a week. To access the presentation, go to www.hdsa.org/ll. You can also find HDSA's Caregivers Corner webinars at www.hdsa.org/ccorner. And now I'm pleased to welcome Dr. Kimberly Martin. Dr. Martin is an obstetrician, gynecologist, and clinical geneticist who has been practicing medicine for over 20 years. Her genetics training was at the University of British Columbia, where she was privileged to acquire experience in one of the first predictive testing centers for Huntington's disease. Dr. Martin provides consultation and prenatal testing for couples who are at risk to have a baby with a variety of genetic conditions and birth defects. She considers it a privilege to work with these families, and we consider it a privilege to have her. Now, I'm pleased to welcome Dr. Martin.
Hello, and welcome to the Lunch and Learn webinar. I was very pleased to be invited to give this presentation, and I look forward to being able to hopefully answer questions at the end. And we'll go to the first slide. So we're going to start with just a little tutorial about basic genetics, and I apologize to those of you for whom this is old information. Basically, our bodies are just a conglomeration of billions of cells, and every cell in our body contains the complete blueprint that makes us who we are. Our genetic information is packaged in things called chromosomes. And in the usual situation, every cell of our body contains 46 chromosomes, which we can arrange in 23 pairs. And the first 22 pairs, 1, 2, 3, down to 22, are common to men and to women. And the 23rd pair are called the sex chromosomes, and they come in two varieties, X and Y. And when I look at this particular graph or picture of chromosomes, what I can tell you about this individual is that they have the right amount of genetic material. It looks like it's packaged correctly, meaning each chromosome pair is about the same size, and these little dark and light bands match up. And I can tell you that this individual is male because this individual has an X chromosome and a Y chromosome. The actual genetic code, however, is not visible in this picture. What we're looking at is the packaging. The genes themselves are like a string of beads located at various locations on these different chromosomes. So I can't tell you what color hair this person has, how tall they are, or really much more specific information about them. So how do we pass on our genetic information? Well, our chromosomes actually have to go through a process of pairing. So the 1s, the 2s, the 3s pair up, just like in that other picture, and then they split. So a woman puts one copy from each chromosome into her egg, which in the usual situation, of course, would represent 23 chromosomes. the dad puts half of his chromosomes into the sperm. And of course, women have two X chromosomes. So they will put one of their two X's into each egg. Fathers will put an X into half of the sperm and a Y into the other half, which is how the father determines the gender of the baby. If an X-containing sperm gets to the egg first and fertilizes it, the resulting child will be a girl. If it's a Y sperm that gets the job done, it will be a boy. So at fertilization, the egg and sperm get together, and you're restored to the normal number of chromosomes, which is 46, half from mom and half from dad. As you can imagine, we have no control over which chromosomes we give our children. That's happening really without our realization. And that is sort of human reproduction in a very small nutshell. That fertilized egg, then, containing the normal 46 chromosomes, goes on and duplicates itself and divides over and over and over again and forms the placenta, or the afterbirth, the membranes around the developing baby, and of course the baby itself. So as I said, we really have no control over which chromosomes and hence which genes we give our children. This is a family from England. They're the Giddings family, and they refer to themselves as a rainbow family for, I think, fairly obvious reasons. Mom and dad are of different racial backgrounds, and as you can see, their 4 children, although they all look somewhat alike, they also look quite different. And the characteristics that the children have are unique, and every one of us is unique. What's interesting is in the article, this family has gotten quite a bit of press in the United Kingdom, and what's interesting is when this little girl was born, the family actually felt that she had virtually no characteristics in common with her father, and they, somewhat of a lark, but in fact had DNA testing, which in fact proved that he was the biological father. So I think this family is a really lovely illustration of how our genes can segregate and be exchanged and come together to make each of us as a unique individual. Now this is a little more scientific look at how we inherit our characteristics, and specifically looking at a mode of inheritance called autosomal dominant inheritance. And this, of course, is the pattern of inheritance that's followed by the disorder we're going to speak about, which is Huntington disease, or HD. Because we have 2 copies of each chromosome, we have 2 copies of each gene, and we give 1 copy of each gene to our offspring. So in this particular illustration, we have a father who is affected with an autosomal dominant disorder, which means he has 1 normal copy of the gene and 1 changed copy of the gene. His wife is unaffected, and so she has 2 normal copies of the gene. The normal copies are reflected by small letter Ds. The changed copy of the gene is a capital D. So each time this couple reproduce, there are basically 4 potential outcomes. The mother could pass one of her normal genes. She will always pass a normal gene to her children. The father, however, has a 50-50 chance of passing either the normal gene or the changed copy of the gene. So we would predict each time this couple become pregnant that there's a 50-50 chance that their child would be unaffected or would be affected. An autosomal dominant disease reflects a disorder where only 1 changed copy of a gene is necessary to cause the trait or disorder in the individual who carries that changed gene. This is, however, completely random each time. So there's a 50-50 chance with each pregnancy that the couple would either have an affected or unaffected child. So it's possible for a parent who is affected with a disorder to have all unaffected or all affected or some combination of both. if random genetic assortment is allowed to occur. So this seems like a pretty simple question. How do humans get pregnant? And I've had this chat with my own children, so I'm not going to go over a detailed birds and the bees talk with you all today. But certainly the majority of humans get pregnant through sexual intercourse, which allows an egg and sperm to get together and fertilize and result in the development of a new person. But there are lots of other ways that humans can choose to reproduce. This illustration here is a little bit of a cartoon illustrating that basically you can allow normal fertilization to take place in a woman's reproductive tract. This is the uterus. The uterus is connected to the ovaries, which are these little circles here, by something called the fallopian tubes. And eggs are actually produced in a woman's ovaries. In the normal situation, one egg is produced with each cycle. Sperm is naturally deposited in the vagina and swims up through the uterus and actually meets the egg in the fallopian tube. That's the standard way that it's done. But of course, we know that people can become pregnant through something called insemination. And that can be done allowing a woman to ovulate naturally, to time her ovulation, and then place sperm either in the vagina or usually within the uterus to allow conception to occur in the normal way. You can go from that fairly simple reproductive intervention to actually having fertilization take place outside of the body, what's called in vitro fertilization. And this can also be done in a variety of different ways. Now, why might a couple choose to become pregnant using some form of technology or insemination or in vitro fertilization? Well, there are natural reasons why couples would choose to use some form of technology. Perhaps the husband has a sperm problem that doesn't allow enough normally swimming sperm to reach the fallopian tube and fertilize the egg, in which case either the actual husband or intended biological father's sperm can be placed in the uterus, kind of allowing them to make a little bit of a shorter journey. Alternatively, a husband may not have any sperm at all, and a couple may choose to use a donor sperm. And in some situations, the father may be a carrier for a genetic disease, and the couple would choose to use a non-related donor in order to avoid pregnancy of a child with that particular gene. Similarly, women may not have any eggs of their own, in which case another woman could be given medication to stimulate egg production, and I'll show you some pictures of that in just a minute. But conception could then occur using another woman's eggs with the intended biological father's sperm. And conception can actually occur in a petri dish, just like I'm sort of representing here, following which an embryo can be placed into the uterus of the intended carrier of the pregnancy. This is an ultrasound picture of an ovary that has been stimulated to produce multiple eggs. So because in vitro fertilization is a very intensive and costly endeavor, the goal, of course, is to maximize the likelihood of the couple being successful. And what happens is that the woman is given injections of hormones that cause her ovaries to make all of these little black circles. These little black circles are cysts, and they're something called follicular cysts, and each one of them actually contains an egg. Using a needle, usually through the woman's vagina, each one of these cysts is aspirated and the egg is collected. And following that, that egg can be utilized for in vitro fertilization. In some situations, the egg is placed in a petri dish. This is an actual photograph of a human egg. In some situations, the egg is actually just mixed with a group of sperm, and fertilization is allowed to occur in the normal way, but in a petri dish. However, in some circumstances, in fact, a single sperm is selected, and that sperm is actually injected into the egg. So a sperm is selected, the egg is isolated, the egg is being held by this little probe right here, and a very tiny needle is actually inserted and punctures the egg, and a single sperm is injected. You can just kind of see that here. The external surface of the egg is being depressed by the needle, and then it pops in, and a single sperm is injected. This is called ICSI, or intracytoplasmic sperm injection. Hopefully, after that occurs, that single cell begins to duplicate and divide, just like it would if it was in a woman's body, but this is happening in a petri dish. And these are embryos. So each one of these collection of cells originated from the injection of a single sperm into a single egg and is being allowed to develop. It is then possible to what's called biopsy these embryos. So if a couple are at risk to have a child with a particular genetic disorder, and they would prefer to avoid pregnancy with an affected child, they go through that in vitro fertilization ICSI procedure. The embryos are allowed to grow until there are between 8 and 10 cells, following which 1 or 2 of the cells are actually removed from the embryo. This doesn't hurt the embryo. At this point in pregnancy, each one of these cells is capable of duplicating and dividing and becoming an entire human being. But these 1 or 2 cells can be removed, and the genetic information in these cells can be evaluated or tested for the genetic disorder that the family may be at risk for. And this is called PGD, or pre-implantation genetic diagnosis. Pre-implantation meaning that it's being done before the embryo is placed into the uterus and allowed to implant or attach to the woman's uterus and grow to become a pregnancy. I am sure that most of you are very familiar with Huntington disease. Just briefly to review, the gene for Huntington disease is located at the tip of what we call the short arm of chromosome 4, which is represented schematically in this cartoon. The features of Huntington disease, again, are well known to you, but it is an inherited, progressive, neurodegenerative disorder characterized by movement disorders, cognitive impairments, and personality, mood, and behavioral disturbances or changes. In 1993, so 20 years ago, the actual gene change responsible for Huntington disease was first described. And it is caused by, within a gene, which is basically like a string of beads, something called an expanded trinucleotide repeat, meaning that there are an increased number of these CAG repeats within the gene of affected individuals. All of us have a string of CAG repeats in our HD gene. Affected individuals have more than 36 repeats within the gene. The gene frequency within the Northern European Caucasian population is estimated to be about 1 in 10,000. This is another cartoon just to illustrate in a different way the actual genetic change that results in what we know as Huntington disease. So the gene, as I said, contains within it a string of these CAG repeats, and each of these CAGs in the final protein, the Huntington protein, cause the incorporation of an amino acid, which is a protein building block called glutamine. Up to 26 repeats, or 26 glutamines in a row, results in the production of a normal Huntington protein. However, if that protein becomes expanded with 37 or more of these glutamine residues in a row, the protein does not function normally and is accumulated within the brain and is associated with the physical and cognitive effects we know as Huntington disease. So as we talked about, Huntington is an autosomal dominant disorder, which means that having one changed copy of the gene is sufficient to develop the disease. If an individual has less than 27 repeats of the gene, they will pass on their gene in what's called a stable fashion to the offspring. Meaning, if you have, of course, each of us have 2 copies of the HG gene. If a parent has, say, 16 repeats on one chromosome and 20 repeats on the other, their children will inherit either 20 or 24 repeats. Sorry about that. If a parent has 20 on one chromosome and 24 on the other, each of their children will inherit either 20 or 24 repeats. If, however, a parent has 27 or more repeats, when that gene is passed from parent to child, the number of repeats becomes what we call unstable, meaning the child may actually inherit more than 27 or less than 27 repeats from the parent. The likelihood that the number of repeats would increase is actually higher when inherited from an affected father than from an affected mother. And reasons for that are not entirely understood. Individuals who have between 29 and 35 repeats will not develop HD, but are at risk to pass the gene for HD to their children, which expands to an allele of 36 or greater than 40 repeats, which will likely result in some physical and cognitive effects in their children. Allele sizes or repeat numbers between 36 and 39 are referred to as allele sizes of variable penetrance. Individuals with those allele sizes will probably develop HD, but later in life. Individuals who inherit 40 or more will develop symptoms of HD. So it's possible, of course, to take a blood sample from an at-risk individual and determine their allele size. This is a pedigree or a family tree, if you will. Men are represented both in blue and in boxes for my purposes. Women are in pink and in circles. So this is a wife and husband. As you can see, these numbers are referring to the number of CAG repeats in the HD gene for both parents. So the father in this case has an allele size of 18 and another allele of 21. The mother has 2 allele sizes, one of 12 and one of 43. So in fact, she has Huntington disease. In this case, she has a brother who is deceased. It is possible to test their offspring. And as I explained with basic inheritance, each child will inherit an allele, one of their parents' allele sizes. And if one of the parents has an expanded allele, it may be a larger or smaller allele. We can track which allele children receive by looking at the parents. So in this case, this girl has allele sizes of 12 and 21. So she got the unaffected 12 from her mother, and she got her father's 21. This person has not had a blood test for HD and doesn't know what their allele sizes are. This individual inherited the 18 size allele from dad and inherited a slightly expanded allele from her mother. Her husband, who is unrelated, has allele sizes of 16 and 19. So if this couple are interested in exploring their reproductive options, we would suggest that they meet with a genetic counselor, and we would go over the basic inheritance and the reproductive options that they face. Certainly, they could become pregnant and undergo prenatal diagnosis. This is an ultrasound picture of a very cute baby. You can see the little profile here. This is the baby's spine. Baby's laying on its back. And prenatal diagnosis, or testing of fetal tissue, can be done using two procedures. One is called CVS, or chorionic villus sampling, which is performed at about 10 weeks of pregnancy. Basically, what we're looking at in these ultrasound pictures, on the top here, this is the gestational sac. So the black is the amniotic fluid. This is the baby here. And this gray is basically the placental tissue. And remember, I told you that the cells in the placenta, the membranes, and the baby all come from that original cell. Well, in CVS, if you imagine that a baby is inside of the tennis ball and the placenta is this fuzz on the outside, we pluck some of this placental tissue out using either a needle through the mother's tummy or a little catheter fed up through the cervix. These cells from the placenta are harvested, and they can be subjected then to genetic testing. There is a small risk related to the procedure, and the risk of pregnancy loss is estimated to be less than 1 in 200. A more commonly performed test is called amniocentesis. It is performed later in the pregnancy, so of course the advantage of CVS for many couples who are interested in prenatal testing is that they can do the testing at 10 weeks, have results by 12 weeks, at a point when the pregnancy is often still private. Amniocentesis is done after 15 weeks. It's done with a little needle through the mother's belly, and in this case we remove some of the amniotic fluid that the baby is swimming in, which contains cells that are also reflective of the chromosome and genetic constitution of the baby. This is a bit safer test. We estimate the risk of miscarriage to be less than 1 in 500, but again, it's done a little bit later in pregnancy. Some families would choose to use reproductive technology in order to avoid pregnancy with an affected child. And I'm going to just go through a little bit about ways that pre-implantation, or PGD, can be done for couples at risk specifically for Huntington disease. Basically, of course, they could choose to use an egg or sperm from an unrelated donor, therefore avoiding conception of a child with the particular disorder. However, many couples would prefer to be genetically related to their offspring, in which case they would go through the in vitro fertilization ICSI procedure. The embryos would be grown to the 8 to 10 cell stage, and again, 1 or 2 of those cells would be removed and subjected to genetic analysis. If parents know, I'm going to go back here, if parents know what their allele sizes are, meaning if in this case the mother has had predictive testing for Huntington and knows that she has an allele size of 46 and 18, and we know the allele sizes of the father, in this situation, the type of prenatal testing that would be done would be quite straightforward. The 1 or 2 cells from the embryo would be subjected to analysis for allele size, and only embryos containing unaffected allele sizes would be transferred into the uterus of the woman, and embryos that inherit the affected allele size would be discarded. As many of you know, however, some individuals who are at 50-50 risk for Huntington disease, like this girl here, choose to not be tested. And in those situations, but may in fact not want to take the risk of having an affected child, even though they themselves don't know whether they carry the gene. And it is possible in some families to do testing on embryos without, in fact, disclosing the HD status of the affected parent. In this type of testing, it is typically done using what's called linkage analysis, and I'm going to show you that here. Sorry, I'm going to flip back. We can track allele sizes in an individual, but there are many genetic markers or little different colored flags, if you will, around the Huntington disease gene that can be used for predictive testing. And this, in fact, is how predictive testing was done prior to 1993, when it was not possible to test for the allele size itself. What the laboratories were doing was looking at markers around the gene and trying to decide in each family which marker was associated with the disorder. This is a pedigree that I'm going to kind of work through with you so that you can hopefully understand a little bit of how what's called non-disclosure prenatal diagnosis is performed. Basically, we have a family here, that same family, where the mother is affected with grandmother of the fetus, mother of this gentleman, is affected with Huntington disease. So the hash marks here are indicating affected status. If we can test her, we can look at the different markers around the Huntington disease gene. She, in this case, has markers that are, and because she has 2 copies of the gene, she'll have 2 markers for each site, each little spot around the gene. And in this situation, this woman has 2s, 3s, and 2s at those specific sites. If we draw a blood sample from her unaffected husband, he has different markers at those sites. He has 1 and 3, where she has 2 2s. He has 2 2s, where she has 2 3s. And he has 2 1s, where she has 2 2s. And we can't actually tell which one of these 2 chromosomes carries the HD gene, but we know that one of them does. So for this family, we don't actually test this individual because he does not want to know whether or not he inherited the HD gene from his mother. But he will have inherited one of these chromosomes from his mother and one of these chromosomes from his father. We just don't know which. Now, we do need to know his wife's markers. So she has a 2 and a 1. She has a 1 and a 3 and a 1 and a 2. So what would be done for a non-disclosure prenatal diagnosis for this particular family is that embryos would be created using his sperm and her egg. They would be grown, a few cells would be removed, and the embryo would be tested to see which markers at each site the embryo had. We would then compare these markers with the grandparents. We know that he has 1 set from his dad and 1 set from his mother. If the baby inherits the set that he got from his father, who is unaffected, then we know that his child also, in this situation, got the marker from his father. So the baby turns out to have 3 and 1, 2 and 3, and 1 and 2. We know that the baby has to get either his mother's chromosome or his father's chromosome. And we can trace the markers and conclude that this embryo, who happens to be a boy, got the 3-2-1 from his dad and got the 1-3-2 from his mother. So in this situation, we predict that the embryo received the grandfather's chromosome 4, not the grandmother's chromosome 4, and would be unaffected. We also know, however, that it's possible that this particular gentleman did not inherit HD. So in this type of prenatal diagnosis, it is possible that it's being done and that all embryos are normal. If he didn't inherit the HD gene, of course, he can't pass it to his children. This would be an alternative result, the same family with the same markers, in which case, this time, the baby received the 2-1-1 from the mother and received the 232 from his dad, and because we know the markers that the grandparents have, we know that this embryo got the marker from the grandmother who is affected. So even though we don't know if this grandmother's chromosome has the HD gene or not, this is an embryo that would not be transferred back. So quickly, we're going to just go through current recommendations for HD testing. And I'm going to actually utilize the more recently published guidelines from Europe, which the US guidelines are very similar in. So let's review those briefly, because I do want to touch a little bit on some of the sort of ethical and counseling issues that go into decision-making about reproductive choices and prenatal testing. So in terms of testing adults, current guidelines suggest that it is recommended that the minimum age of testing be 18 years of age. Minors, individuals less than 18, although that age is variable in different countries, who are at risk but who request testing should have access to genetic counseling. They should be supported, given information, including a discussion of all their options for dealing with being at risk. And I think that it's almost impossible to underestimate the importance of counseling and support in the pre-test period of time, and then that support continues through an individual's not just their testing, but their entire lives if necessary. In terms of the testing process itself, unlike most medical tests, it is recommended that someone who is considering and undergoing testing for HD bring someone with them throughout the different stages, both the pre-test counseling, when they have the test done, and the delivery of the results. And this is quite different than the way testing is offered for other genetic diseases. But again, as I was alluded to in the introduction, I was working at the University of British Columbia as a fellow during the sort of introduction of predictive testing. And a lot of research that came out of that particular program indicated the considerable emotional impact both for individuals who choose to be tested, for individuals who choose not to be tested, and the emotional impact of the results, whether affected or unaffected. Of course, all of this should be assessed on an individual basis, and in certain situations, a companion may not be appropriate or required. The counseling unit itself should plan a follow-up protocol which provides support and timing and location for test result disclosure. And HD testing in general is not disclosed, results are not disclosed by telephone, but are disclosed in person, ideally with a companion. Preconception counseling is ideal. Particularly in situations where one partner is either at risk of HD or is known to be a carrier of the gene expansion. And before pregnancy counseling is emphasized because once a woman becomes pregnant, time passes. And of course, certain options are no longer available if a natural pregnancy has occurred. And the timing for prenatal diagnosis is relatively sensitive. And results from prenatal testing can take up to 2 to 3 weeks. It's also hoped that by talking about things before a pregnancy that, first of all, if the at-risk individual hasn't been tested, they can make a decision about whether or not they themselves wish to find out whether they've inherited the gene. And we can also do the groundwork for non-disclosure prenatal diagnosis if that's what a family chooses. And that non-disclosure prenatal diagnosis requires the cooperation of several family members and coordination of testing. And it's an individual sort of plan of testing for each family. So doing it ahead of time is really critical. And we do suggest that individuals who are at risk should be informed of all of their reproductive options. A couple who are requesting prenatal testing should be informed that if they intend to complete the pregnancy, regardless of whether the baby inherited the gene or did not inherit the gene, that there is no valid reason for performing the test. What this is saying is that because the guidelines have been written in such a way that individuals under the age of 18 are strongly discouraged from having predictive testing. If a couple become pregnant and undergo prenatal testing, they will then know the child's status. And if they choose to continue the pregnancy, they will be faced with having to decide how or if to ever disclose that information to their child. If not to disclose the information, then one would question why knowing prenatally was even valid. On the other hand, if for some reason they would choose to not follow the guidelines and divulge this information to their child, they've then taken away the child's right to decide whether or not to find out. And many at-risk individuals choose to not be tested for Huntington disease. And a parent has then, in a sense, bypassed the child's right to not know their status. There is also a small, but not zero risk of miscarriage related to both the CVS and amniocentesis procedures. Reproductive choice is something that many people feel is important. And in most developed countries, parents are given the responsibility to make decisions for their children which they believe are best and consonant with their value system. These choices are usually extended into the prenatal preconception period. A woman or couple may choose to have their babies tested for many different genetic conditions, including gender. A woman or a couple may choose to continue or interrupt a pregnancy for a number of different reasons, which may be economic, may be social, or due to the presence of certain birth defects or genetic conditions. I believe that it is very important that a woman and couple are provided with this type of information in a way that they understand, that they're provided with that information in a timely fashion, and again, ideally before a pregnancy is conceived, and are supported, if not by just a genetic counselor, but particularly by someone who has experience supporting, counseling, and working with families who have been affected by this disorder. Well, how much does it cost? I do not, in fact, do any type of reproductive technology. I do prenatal diagnosis and counseling, but I did do some Googling, and much of this information actually comes from the CDC, which has information about sort of average costs, recognizing that costs through any one particular provider may be quite different and may somewhat vary regionally. Artificial insemination, this would be used, of course, when a father is at risk to have HD, is the least expensive option. This would be insemination with donor sperm with an average cost of about $1,000 if some medication for the wife is needed to time ovulation and insemination. A cycle of in vitro, meaning that the woman is given medication to stimulate her ovaries, the ovaries are removed and allowed to fertilize, costs anywhere between $8,000 and $15,000. The likelihood of becoming pregnant with one in vitro with one IVF cycle varies between 20 and 60%, depending upon underlying medical or fertility issues. If the couple plan to do in vitro fertilization and utilize prenatal genetic or pre-implantation genetic diagnosis, or PGD, ICSI has to be performed. So if a couple wish to have their embryos fertilized outside the body and tested before they're put back, the cost would include about $8,000 for the IVF, potentially additional $3,000 to $5,000 for the medications to stimulate the ovaries. The sperm injection into the egg averages about $1,500, and an additional $3,000 to $4,000 to biopsy the embryos. Replacing the mother's eggs with a donor egg on average costs about $12,000. Obviously, with in vitro fertilization, multiple embryos are hopefully created. A maximum of 2 to 3 embryos would be replaced. Couples have the option to have remaining healthy embryos frozen to be transferred at a later time for additional pregnancies. And saving the embryos has an upfront cost of up to $1,000 and then an annual storage fee. So I'm going to stop here, and I'm looking forward to hopefully answering some questions. Family planning in Huntington disease, really the most important word there is planning. And although we estimate that up to half of pregnancies in the United States are unplanned, I hope that the importance of preconception counseling and planning can be emphasized. I think it is very important that at-risk individuals meet or speak with genetic counselors or health professionals who have experience with HD, again, ideally before pregnancy. It's really important that you understand your options. And the main options we've talked about today are natural conception with prenatal testing, in vitro fertilization with pre-implantation genetic diagnosis, and the final is sperm or egg donation. I did not list adoption here, but of course some families do choose to pursue adoption, which I guess is another form of sperm and egg donation. So I'm going to stop there. This is my last slide, and I thought this was a really nice illustration, and I hope that for some of you participating in the webinar today that the information has given you hope for the future. And I'm going to stop there, and I'm going to click on a little button here. I apologize. I haven't done a lot of these, so I'm not quite as facile with the questions as I would like to be. So let's see here. Looking for questions. Jane, I don't know if you can hear me or not, but I'm not seeing any questions. Maybe there aren't any questions at this point, which is fine.
So, Dr.
Here
Martin, I believe there are 2 questions. Do you see them?
Yes,
Great.
I do now. Yeah, sorry. Okay, so how often is, so here's the first question. How often is non-disclosure prenatal testing done? You know, that's a really good question, and I don't know the relative frequencies by which you know, non-disclosure versus disclosure prenatal testing is done. I don't, and when I did up my literature review for this, I'm really not, I don't think I really came across an accurate breakdown of that. Certainly both are possible, and it's just important that communication is begun as soon as possible to make sure that the necessary information is in place to allow that to happen. Next question, do I know the cost of CVS? Where do you find it? Okay, so CVS, chorionic villus sampling, the procedure itself, again, this varies, the cost varies with location. For example, I do CVS in my center here in St. Louis, and the out-of-pocket cost for just the procedure itself is upwards of about $500. It can be, certainly it is usually covered by health insurance unless maternity coverage is excluded from your plan. But certainly we have couples who choose to have prenatal testing and do not go through their insurance, and we do usually offer some discount in that situation. CVS is usually performed by either a maternal fetal medicine specialist or an obstetrician geneticist. And so if you can, I suggest that if you're looking for a center close to you that does CVS, that you contact perinatal or maternal fetal medicine centers in your location and find out whether they offer CVS or not. It is not all maternal fetal medicine specialists do not perform CVS. They all perform amniocentesis. It is important that CVS is done by someone with experience with the procedure, because it is technically a little different than an amniocentesis. Next question. Let me just read this. No. Again, if one grandparent has HD and the child does not inherit, does this mean the grandchild? Okay. So, yeah, I know. The non-disclosure PGD it is complicated. And the way I think about it is, for my chromosome 4s, and I got one from my mother and one from my dad. If my mother has a disorder on her chromosome 4, there's a 50-50 chance that I got the normal gene or the change gene. When I make an egg, I either put the chromosome 4 from my dad in it or the chromosome 4 from my mom in it. If I give my chromosome 4 from my dad, I know I can't give the change gene, because my dad doesn't have the change gene. If I give the chromosome 4 from my mom, there's a 50-50 chance that it's the HD chromosome. I hope that's clear. So if I give my dad's chromosome 4 to my child will not develop Huntington disease. If I give my mom's chromosome 4 to my child, the child may develop Huntington disease. But if I got my mom's normal chromosome 4, I can't give Huntington disease to my kids. But the only way I know that is if I have predictive testing. I hope that's clearer. Are there risks with ICSI or PGD for the mother or child? So that's a really good question. So with in vitro fertilization, the woman's eggs, ovaries are stimulated. And although they monitor the ovarian stimulation very closely, sometimes the ovary becomes hyperstimulated, and that can lead to something called hyperstimulation syndrome, which can often be managed conservatively with bed rest, pain medication. It's very rare that, in fact, there's a life-threatening complication. There's a small risk of bleeding related to the harvesting of the eggs. There are some, so in terms of the mother, there are some risks. There's certainly discomfort. It's certainly very labor intensive. And definitely a couple who are thinking about this type of procedure should have a consultation with an infertility specialist so that they can go over those specific sort of pros and cons. In terms of the offspring resulting from pregnancies conceived with in vitro fertilization / ICSI and PGD, the literature is a little mixed. 3% of kids are born with some type of birth defect or learning problem. That's actually the background risk for everybody, even when you do everything right. You know, human beings are complicated, and I tell my families that the fact that a sperm and an egg can get together and it turns out right 97 times out of 100 is pretty miraculous, really. Whether or not there's a slightly higher risk for birth defects in general related to the in vitro process itself is a little controversial. It's certainly no more than 1 or 2% additional risk, and may in fact not be increased at all. The studies are mixed. There are some very subtle genetic alterations that have been reported, and it's too complicated to go into in this scope. But in kids that are conceived through ICSI, the injection of a single sperm. But again, the likelihood of that is considerably less than the likelihood of in fact, the child inheriting an autosomal dominant disease, which is 50%. So, and again, I think these are questions. It's a great question, but something a little more complicated than I can really address in the scope of this. I think I've covered all the questions. I have to say it's a little frustrating to not be able to talk to everybody. Here we go. Oh, here's some more. So this is an interesting question. Does knowing what your status is affect the likelihood of passing the gene to your embryo? I'm not aware that it does. I think that it really, it's a great question. You know, we try, I think as a healthcare community, we've really empowered women in particular that, you know, if you just take care of yourself and you eat right and everything, that your pregnancy will be healthy. In fact, we really don't have any control over how we pass our genetic information to our children. And no, I'm not aware that knowing your status can affect the likelihood that you would pass the affected or the unaffected allele, but that's a really good question. We just have a few minutes left, and you can certainly email questions. If you go to the hdsa.org website, you can email to J. Kogan, and I'm very willing to answer questions offline. So feel free if you do see something. This is an important one, asking about insurance status. So there is something that I encourage everyone to familiarize themselves with. It's called the GINA Act, G-I-N-A, and the government has a nice website, GINA.org. If you Google it, it's the Genetic Information Non-Discrimination Act, and in fact the results of genetic testing cannot be used to determine your insurability or your healthcare insurance premiums. So in fact it does not affect your insurance status. They can ask about your family history, but they cannot inquire about results of genetic testing. It only, however, at this point extends to health insurance, not life or disability. But that's a good question, and I should mention that, and I encourage people to familiarize yourselves with the GINA Act. So this is good. So if I'm not supposed to disclose that I've been tested for HD, so I'm not a lawyer, I'm not an insurance attorney, but I do know that if you do not tell the truth, or if you answer a question on an insurance questionnaire and you lie, your insurance can be canceled. And I would encourage, particularly with the Genetic Information Non-Discrimination Act, insurance companies should not be asking about results of genetic testing. Again, this issue relates to submitting bills for genetic procedures and that sort of thing. I think that would have to be looked at on a case-by-case basis. But as I said, your insurance company is not allowed to discriminate based on results of genetic testing.
Dr. Martin, I'm so sorry, this is Jane
Yep,
Kogan,
I think
we
we're
are
done.
out of time. Thank you everybody for attending, and just a reminder that you can email questions to me for Dr. Martin at jkogan@hdsa.org. And I also just want to let folks know that HDSA does have a section of the website and several webinars on the Genetic Information Non-Discrimination Act that you can find at www.hdsa.org/GINA. Thank you so much.